My name is Justin Kruger. I'm currently a postdoc with the Stanford Space Rendezvous Laboratory. Today, I'm presenting on on-orbit performance and lessons learned for autonomous angles-only navigation of a satellite swarm. These are some results from the recent Starling Formation Flying Optical Experiment, part of the NASA Starling mission, which I'm excited to share today. Okay, so let's start off with the motivation behind this work, where there is a need to be able to determine the orbits of known or unknown, cooperative or uncooperative resident space objects, or RSO. And the question is how we can navigate multiple RSOs in a way that's autonomous and scalable without relying on something like GNSS for space situational awareness, on-orbit servicing and debris removal, and applications like resilient and deep space navigation. Now, an attractive solution here is angles-only navigation, as pictured on the right, where we have cameras on observer spacecraft measuring the bearing angles to other system members. Navigation then becomes self-contained in the system. Cameras themselves are ubiquitous and accurate, quite low size, weight, power, cost sensors. However, bearing angles do present weaker state observability. They don't give us direct target range information, and we also then have to deal with optical visibility constraints. So, despite this, two prior flight experiments have demonstrated angles-only navigation in flight, Argon in 2012 and Avanti in 2016. It's important to note both of these experiments were very successful, with varying degrees of onboard autonomy. However, they were also characterized by some limitations, namely, they only handled a single observer and single target. They relied on maneuvers to help resolve the target range. They relied on having some target orbit knowledge to initialize, and also relied on GPS to maintain the orbit estimate of the observer spacecraft. And in response to this, the Stanford Space Rendezvous Lab proposed the Starling Formation Flying Optical Experiment, or StarFox. Really, the goal was to build upon the successes of those previous experiments and also remove their key limitations to enable new types of distributed missions. So now StarFox is operating 4 satellites, almost entirely autonomously. So next, let's talk about the navigation architecture being applied here, which is the Absolute and Relative Trajectory Measurement System, or Artemis. A kind of typical Artemis system is on the bottom of the slide here, where instances of the Artemis software are deployed on one or more cooperative observers to track one or more non-cooperative targets. And some key features are that it is angles only, so we get bearing angles from the onboard cameras for navigation. It's distributed, so different observers might be estimating a subset of the complete swarm state. It's cooperative, so optionally, if there's a crosslink available, the observers can share measurements with each other. It's autonomous, so requires minimal external interaction and is miniaturized, so it is suitable for small spacecraft hardware. Okay. So here's a very high-level block diagram of the Artemis system. Some key things to know here are that the sources of measurement information are in gray. For example, the vision-based sensor in the top left there. The exchanged information is in blue, and there are 3 core software modules in green. So we have image processing, or IMP, which runs about once per minute in low Earth orbit. We have batch orbit determination, or BOD, which runs around once per orbit, and sequential orbit determination, or SOD, which runs around once per minute as well. And I want to go through what each of these algorithms does at a very high level to give you an idea of what they're doing. So starting with IMP, the goal is to process images and track potential targets in view to produce batches of inertial bearing angles to those targets for navigation. So IMP does this by starting with an image from the onboard camera. It applies some relatively standard image processing algorithms to, for example, detect stars, and produce a list of bearing angles to any unidentified objects in view, which could be our target spacecraft. Now, the key thing with Artemis is that we want to be able to track these spacecraft without necessarily having an idea of their relative orbit. So the way we do this is we apply... Okay, well, we'll see if this shows up.
Very faint. Yeah. It's like fading in, it's coming.
Interesting. Oh, okay. The way we do this is we apply multi-hypothesis tracking to enumerate and propagate all the possible target tracks we can form from those unidentified angles. So multi-hypothesis tracking, it's quite robust, but it is costly in theory for a spacecraft processor. So what we do is we realize that we have a lot of knowledge about how targets should be moving in the camera image due to relative orbit dynamics. So we can apply parametric models of target kinematics to those target tracks and use that to select the most physically reasonable tracks and prune the unlikely tracks for efficiency. So in this fashion, we can converge to the correct hypothesis with or without target state knowledge. Next, we have the BOD system, where given these batches of varying angles, we want to produce initial orbit estimates for our targets on board. So the way we do this is we start by considering a batch of varying angles y across a set of epochs, which depends on the system state x at some time. And the issue we face is that target range is weakly observable with varying angles. And the way we treat this is we define some kind of relative orbit element estimate x initially, which corresponds with a set of samples of delta lambda. And delta lambda is the relative orbit element which most closely corresponds with that weakly observable target range. And for each of these samples, we compute this residual, or the difference between the measured bearing angles from the camera and the bearing angles that we model based on this estimated state. And over time, we can then update the state to reduce this residual using something like iterative batch least squares. And the goal is to produce a plot something like this, where on the x-axis we have our delta lambda samples, and on the y-axis we have those measurement residuals. And we can pick as our output the sample that produced the lowest measurement residual. So we're kind of exploiting the relative orbit element state here by dividing the state into the strongly observable and weakly observable components. Another thing to note is that we can use these converged measurement residuals to actually estimate our initial state uncertainty as well. So finally, we have the SOD system, where given that state initialization, we want to refine it over time using new measurements from the onboard camera, as well as any remote measurements we might be receiving from other observers in the system. So in SOD, we apply an uncentered Kalman filter with orbit element states, nonlinear dynamics and measurement models to retain a lot of the higher order information that's needed for angles-only observability. We can also actually structure the filter in a smart way to make it more efficient on board and reduce the number of calls we have to make when computing sigma points in the uncentered Kalman filter. Another important note is that if we have multiple observers available, we can use that for distributed stereo vision. In that case, we have a number of data association algorithms to match measurements from different observers of the same target, which provides you with a lot more geometric information and improves the accuracy and robustness of the state estimate. Finally, we have a couple extra features, things like adaptive process noise estimation, auxiliary state estimation for things like drag coefficients and clock offsets on board to really try and improve the long-term robustness and autonomy of the system. Okay, so that's a quick introduction to Artemis itself. Now let's get onto on-orbit performance. So Artemis is currently flying on NASA Starling, which is a swarm of 4 CubeSats in low Earth orbit, which launched in July 2023. And Starfox applies the onboard star trackers and crosslink radios to perform absolute and relative navigation for the swarm. So each CubeSat carries 2 star trackers, an S-band radio, a payload processor, as well as a GPS receiver we can access, and 4 cold gas thrusters for propulsion. So I wanted to talk about and introduce 2 kind of key flight results that illustrate the first time some of these capabilities have been actually demonstrated in orbit. The first is an autonomous initialization. So we detect and begin tracking a target in view, which is unknown to us, so we don't have any a priori target orbit knowledge, but we can start navigation, which is very useful for something like a space situational awareness application. So here we have a video, actually, where on the left you can see images from the onboard star tracker, which are passing through the image processing system and are being classified as, for example, the yellow objects are stars here, and the green in the center of the field of view is a detected swarm target. So initially, the system is doing independent multi-hypothesis tracking, and after about 5 hours, it passes a batch of 40 measurements to the batch orbit determination system. So that computes an initial state. The BOD range estimate is in red here on the bottom right, so you can kind of see the target is around 80 kilometers away here. And then we pass this to the SOD system to start refining the state using new camera measurements. So that's shown in the blue here, where the blue shaded region is the amount of state uncertainty. In this case, it's the relative position of the target in the RTN frame. And the blue line shows the amount of state estimation error. So I guess a thing to notice here is that we get a lot of initial error in the tangential direction specifically, around 10 kilometers of uncertainty, which is, that corresponds to that weakly observable range. So it's what we expect. But we can refine that very effectively over time with new images to reach a kind of final steady state uncertainty, which is around 1% of the intersatellite distance. We're also able to do this in the presence of quite large measurement gaps. So the gray sort of bars here are where we're actually getting new camera measurements. So we're able to keep tracking the target through quite significant measurement outages. Another key result here is actually trying to conduct autonomous absolute and relative orbit determination using only bearing angles. So in this case, we're tracking multiple targets with multiple observers, which gives us more observability and allows us to maintain an absolute orbit estimate without requiring GPS updates. So this is useful for kind of a deep space autonomy scenario. So here we have another video where in the top left here, you can see that the relative orbit paths of the three swarm members involved in this experiment, where a black line indicates that a measurement occurred between those two spacecraft. Below this, in the green, you can see the absolute position estimation from one of those swarm observers, where, again, we start off with quite a large amount of initial uncertainty here on the order of several kilometers, but we're able to slowly refine that over time through the virtue of those multi-observer bearing angles and the improvements to observability that they produce. Below this, in the red and blue, you can see the relative position estimates for two of the targets being tracked by this observer. So we can do absolute and relative estimation simultaneously. And another thing to note is that compared to a similar single observer case, we do get increased performance here because the multi-observer bearing angles give us a lot more geometric information to work with. So ultimately, Star Fox was very successful. Here is sort of a summary of a few of the key performance parameters we defined pre-flight. And we were able to achieve all of these either through in-flight experiments or by post-processing the flight data on the ground. These are discussed in a bit more detail in the paper, but we did demonstrate a number of firsts for optical angles only navigation in terms of the multi-observer and multi-target experiments, initializing navigation for unknown targets, simultaneous absolute and relative orbit determination, and long-term convergence of a maneuver-free state estimate. However, despite those successes, we did have to deal with quite a few problems in orbit, and this is also part of the valuable lessons learned from this flight experience. So one of the key issues that we faced was that target visibility was much worse than we expected compared to what we computed pre-flight. You can kind of see this in this image on the bottom left, where the target labeled SV3 is fairly consistently visible, but SV2, which is further away, is not always detected by image processing. And we found that in practice, the maximum visible distance was around 130 kilometers, where we'd sort of assumed visibility up to around 200 kilometers before flight. And that meant that even though we were taking images every minute, in some cases we only observed a target maybe 20 times over 12 orbits. So we had very sparse measurements in some cases. Another issue that we faced was that initially when we were developing Artemis software, we could verify it using a camera in the loop testbed, pictured on the bottom of the slide here, where we could stimulate an actual star tracker, the same model we were using in flight to generate realistic inputs. But we couldn't apply the same process during integration and testing of the spacecraft itself due to some resource limitations, and that meant we couldn't really exercise a lot of execution paths when running on the spacecraft before launch. Um, so this led to some issues. So in flight, we had very high processor load, which led to some missing image measurements. Also, some desynchronized timestamps between GPS and the star tracker, which manifested as, a roughly 400 millisecond offsets between the star tracker and GPS, led to this state estimation error in the along track direction of several kilometers. And we also had some more general issues with measurement quality, things like very large GPS velocity uncertainties, as well as many hot pixels in the images as well. Despite this, Star Fox was able to be very successful, I think because of two reasons. One is that we had a digital twin of the flight software, so we could save all the navigation inputs we were getting in flight, pass that data through a software emulator on the ground, and very quickly reproduce and troubleshoot this on-orbit behavior. And also the software design was fairly robust, so we had many tuning parameters we could fiddle with to address these issues, fallbacks in case of missing measurements, which meant Artemis was quite flexible when dealing with these sort of unexpected anomalies in flight. So I wanted to finish today by talking a bit about next steps. So, in summary, we have Artemis. We enable autonomous angles-only navigation for varying multi-agent configurations. And we've initially verified this during NASA Starlink experiments, which are some of the first demos of autonomous vision-based swarm navigation. A lot of valuable experience in terms of the lessons learned. And of course, huge thanks to the NASA Starlink team for their support. But we are also exploring many other research directions, support for cislunar navigation, for rendezvous and proximity ops. The success of Star Fox has led to a Star Fox Plus extended mission beginning next week. And also, this concept we call Falcon, which is an alternative PNT SSA system, which aims to fuse on-orbit imagery with space catalog data. And this is the last one I want to talk about here. So it's kind of a quick preview. We have Star Fox Plus, which is going to extend Star Fox with 5 algorithmic extensions with new capabilities. And the one I wanted to kind of focus on as a demo is RSO identification. So using space catalog data to identify transient resident space objects in the camera image. Now, one of the things we noticed in Star Fox is in these images, the image processing system is classifying a lot of objects as unknown or unidentified, which are the red squares in these images. And we sort of wondered what they were. And one of the possibilities was that they are other satellites or space debris passing through the field of view of the camera. And what we wanted to try and do is actually see if we could usefully utilize that information and identify these objects. So we've developed a new system where we can uplink space catalog data to the spacecraft. When it gets a new image, it will propagate that data to the current image time and estimate the positions of all those catalog objects and try and match them up to unknown objects observed in the image. And whenever this video pauses, one of the sort of white ellipses indicates a possible match between a catalog object location and an observed object in the image. So the question is, we can maybe identify these objects in flight, which is very useful for something like a space situational awareness application, getting new measurements of space catalog objects. But we wanted to extend this into something we call Falcon, or fast autonomous lost in space catalog-based optical navigation, where if we identify these objects, they are then acting as essentially beacons with known positions with respect to the observer. And we can use those beacons to actually triangulate our own position with respect to the other objects and use them to help with essentially autonomous optical orbit determination for the observer spacecraft. So this is kind of a quick preview of where we hope to take Star Fox and Falcon in the future. And yeah, that's all I have today. Thanks for your attention. Happy to take any questions.